Good afternoon, everyone. So we have an exciting session starting. My name is Alexandra Boltaseva, and I'm Professor of Electrical and Computer Engineering and Materials Engineering from Purdue. I also represent Purdue Quantum Science and Engineering Institute. I'm involved also with one of the DOE-funded quantum centers, and I lead workforce development efforts at Quantum Science Center, which is led by Oak Ridge National Lab. And I also have a privilege and honor to be a faculty representative from Purdue side for Chicago Quantum Exchange. So thank you for having me here. I'm very excited to chair this session this afternoon. And it gives me a distinct honor to introduce our very first speaker for this session. Dr. Charina Chou is the Chief Operating Officer at Google Quantum AI. And she oversees technical operations, business strategy, public engagement, I guess pretty much everything at Google AI. Previously, Charina led public policy communications for emerging technology at Google and also served as a White House Fellow for the US Office of Science and Technology Policy. Charina holds a Bachelor in Chemistry from Stanford University and PhD in Physical Chemistry from UC Berkeley. Please welcome Dr. Charina Chou.
Hi, everyone. I am here to talk about Google's perspective on the journey to a quantum computer. Our journey is inspired by this quote from Richard Feynman. He made it over 40 years ago. The key point of his quote is that nature isn't classical. Right? At its heart, and we've heard this several times today, at its heart, nature is quantum mechanical. If you want to make a simulation of nature, you'd better make it quantum mechanical. The real question for us was, can you do that? If so, how? And what could you actually use it for? And this is an image of artwork that actually hangs in our lab. Many people in Google Quantum AI are nature enthusiasts. We've got people who love to hike, who love to ski, swim, bike, run, all sorts of things being outside in nature, and there are a lot of really intriguing things that we wanted to understand. First of all, is it possible to actually understand nature at a more fundamental level, to really understand what is going on with atoms, electrons, molecules at their heart? And then secondly, could we actually be inspired by nature? Could we take these elements of nature and actually learn how to engineer something that has not yet been created? Now, Richard Feynman's quote has turned out to be prescient, and I will make a couple of comments here. First, I think as we all know, and again, some of the comments have been made today, classical computing continues to make progress. You can see one measure of this here on the screen. We see that the ability of classical computers, both in terms of the software and the hardware, continue to grow. And we also see that there have been enormous advancements in AI. And I'll take a couple moments here to share some thoughts. We often get this question, why is the name of Google's quantum computing division Quantum AI? Why Quantum AI? Why not just Google Quantum or Google Quantum Computing? And I think there's a couple of reasons for this. At its heart, Google has always been a computing company. Classical computing and AI have been enormous strengths and areas of investment for Google. And we've always thought, the thesis was from the beginning of the start of Google's quantum effort that quantum computing and AI would really be symbiotic, would be mutually beneficial, and that we could help each other in these fields. So, for example, we are using a lot of AI to help us with automatic image recognition as we look at our wafers as they come off the line. Right? We're using AI for automatic software coding and improved calibration techniques. We also see on the flip side that quantum computing might be able to help AI. So are there opportunities for quantum machine learning, that is learning from quantum data, learning from data that comes from quantum sensors? And we've seen over the last few years that, yes, this really does seem to be a possibility. Certainly, there's also a holy grail of looking for opportunities in classical optimization, classical machine learning using quantum computers, and we will look for that, right? And you can see here on the screen a couple of examples, right? Both in analysis as well as generation. A lot of the Nobel Prizes that we saw recently this year, and then on the hardware side too, new chips specialized for AI. right? But the punchline of the Richard Feynman quote is that despite all of these advances in classical computing, right, and which continues to advance, right, despite all of the great progress in AI, some problems are still beyond even the best classical computers. So, one example here on the slide, right? You can see methane, ethane, propane, right? Respectively take a order of seconds on a CPU to calculate the electronic ground state, minutes, and then days for propane, right? And as you extend beyond that, right, many people talk about FIMOCO as this quintessential molecule of, could you really understand what is the electronic ground state of FIMOCO? This is involved as an enormous catalyst, which could have opportunities for things like fertilizer production. Could we really better understand FIMOCO? And some of the current thinking all points to this idea of, yes, quantum computer would be a tool, even if it's impossible, even with all of the advances in classical computing and AI, to understand ground state of FIMOCO, let alone dynamics, quantum dynamics, interactions, things like that. What would that look like? Could we use a quantum computer to achieve that? Key point here is that quantum computing is fundamentally different from classical computing, right? And this is really what opens up new opportunities. If you look at all classical computing over the history of thousands of years, right, from abacus all the way to data centers today, as different as they are, they have fundamental logic in common. They all operate according to Boolean logic. And this means that simple operations, or even complex operations, right, things like multiplying two numbers together or two tensors together, they are fundamentally the same type of operations that are run whether on an abacus or in a classical data center. Quantum computers are not that way, and that's what opens up new opportunities. And all of this is really what drives us at Google Quantum AI. Our mission is simply stated as this: to build quantum computing for otherwise unsolvable problems. I'm going to focus on the two components of this mission statement in my remarks, and then have a last section at the end on one thing that is critical to achieve this mission. So first part, how do you build a quantum computer? This is a question I know many people in this room are thinking about. Certainly many of us at Google are thinking about this, and we have lots of collaborators all thinking about this question. In 2016, our team really set out to identify what a roadmap could be towards a workable, fault-tolerant, large-scale quantum computer. And what we said was, what is the end state we want to get to, right? We're seeing lots of progress in all different realms. We're seeing lots of new papers and ideas coming out, but where do we as a field want to get to? Where do we as a company want to get to in terms of quantum computing? And you can see this endpoint here on this screen. We looked at what was necessary for things like the calculation of FIMOCO, and it turned out that you would need, and we've seen this in a couple of quotes today, at least something like 10 to the 6, 1 million physical qubits, with logical error rates of something like 10 to the minus 10, right? Both of these are important. Sometimes we hear just about the quantity of physical qubits. You've got 100 qubits, 1,000 qubits, million qubits. That's fine, but the quality also really matters. So looking at both of these things together, how could we get to 10 to the 6 physical qubits, 10 to the minus 10 logical error rate? That was our North Star in terms of what we wanted to build. And it seems like, especially from latest literature, this is something that could be capable of calculating something like ground state of FIMOCO. You'll notice here, of course, the arrow doesn't stop at 10 to the 6 and 10 to the minus 10 physical qubits and logical error rate. There is an arrow that goes to the right, right? Of course, like the history of computing, you imagine it would keep on going. But this was a clear North Star, clear endpoint that we wanted to work towards. So how do we get there? One of the things we noted for the number of physical qubits was that it was, again, on order 10 to the 6. So could we work backwards and find points along that line that would serve as intermediate milestones all the way to this error-corrected quantum computer that we want to build? So we really broke it up into milestones going along with the order of magnitude of the number of physical qubits. So you can see starting at the very beginning, 10 to the 1, 10 to the 2, 10 to the 3, 4, 5, and then getting to 10 to the 6. We also identified accompanying logical error rate that we wanted to try to get to at that number of physical qubits. We called all of these milestones. So we have milestones 1 through milestone 6. We wanted to identify what would be needed at each point. So milestone 1 this was mentioned in the earlier panel as well, this idea of a beyond classical benchmark with order of 10 to the 1 physical qubits, would it be possible to actually perform a computation on a quantum processor that is impossible, beyond what is possible on the world's best supercomputer? That was an open question. It was one that we saw coming from national academies and lots of other places. We identified this as the first milestone we wanted to have on our roadmap. Milestone 2, this idea of a logical qubit prototype. All right, so when you get to the order of something like 10 to the 2 physical qubits, could you actually start to build a prototype of a logical qubit? What does that mean? Well, we all know, those in the field know that every single physical qubit has an error associated with it, right? You're never going to have a physical qubit that is perfect. So as you start to scale and get more and more physical qubits together, you're increasing your number of qubits, but you're also increasing the error, right? And that brings down what your possible capabilities are for your processor. So we wanted to be able to start to scale, add more qubits, again, on the order of 10 to the 2 physical qubits, but show that as we added more qubits, we were actually bringing the error rates down. And our target logical error rate for this was something like 10 to the minus 2, 1 error in every 100 algorithmic steps. Milestone 3, we identified as, all right, let's say that we've got now 10 to the 3 physical qubits. Could we get to this benchmark of 10 to the minus 6 logical error rate? This is what many have identified as, maybe starting point for interesting algorithms. Could we start to achieve that in this near-term scale? And we call that one long-lived logical qubit. Milestone 4, could you actually start to get a bunch of these logical qubits to talk to each other and get communication between them? And then milestone 5, how do you start to scale up all of those modules together such that you're now clearly on your way to milestone 6? So milestone 1, this is a beyond classical benchmark. As I mentioned, this idea of could you actually demonstrate on a quantum processor that you could run a calculation that was impossible to run even on the world's best supercomputer. You can see here one figure from our paper in Nature 2019. You can see we actually used an algorithm called random circuit sampling. This was developed over a few years and was really identified to be an opportunity that quantum computers, even today's, could be great at, and maybe it would be difficult as the computation became larger and larger. And you can see the punchline here, which really was at its highest depth that we were able to go to. It would take about 200 seconds on our quantum processor, what was expected and calculated to take 10,000 years on the best supercomputer at the time. I have another Nature paper citation on the screen from 2024. Actually, it's just from 2 weeks ago, which we published. It's basically the latest version where we've expanded quantum volume of our random circuit sampling algorithm and showed that really this problem is now exponentially hard for classical supercomputers. So we achieved that milestone. The next one was this one I mentioned, milestone 2, a logical qubit prototype. And this was something that we showed in Nature, published last year in March, and we really looked at what would be possible, right? As we start to add more and more physical qubits, can you start to bring down the error? And you can see in this graph here, the red lines are at a distance 3. The blue lines, data points, are at distance 5. So it's a very slight, very slight difference, but you can see the distance 5 actually have slightly less error than distance 3, and for us, this was a sign of the first element of what would be needed for quantum error correction. So what are we working towards next? We are working towards what we've called milestone 3, one long-lived logical qubit. So a way to think about it is here on this screen, you can see code distance on the x-axis, also number of qubits, right? So they're correlated. And then on the y-axis, logical error rate per cycle, right? So lower logical error rate is better. You can see the data points from milestone 2, right? That's the distance 3 and distance 5 data points, and you can just see the slightest negative slope there, which shows error comes down. What we are working towards for milestone 3 is actually getting to below 10 to the minus 6 logical error rate per cycle. And this is 4 orders of magnitude difference from what we published in Nature last year. You can see these lines, which we are using as benchmarks to really track our progress. We've identified a metric that we call lambda, which is really the slope of the line, right? What is the ratio of the code distance, the error at different code distances? And as you actually move to larger code distances, can you get to lower error faster? We think this is really the way to get to logical error rates that matter. I'm working very hard on this, hope to have more to share in the next few months. So this is our roadmap, right? And I think, as I said, we're working towards milestone 3. We get asked this question a lot. When do you hit milestone 6? Like, how long does this roadmap take? Is it within 3 years, 5 years, 10 years, right? And it's science. You never predict exactly, right? Nobody knows. But what I can say is that we hope to get to something like milestone 4, multiple logical qubits talking to each other, by 2030. All right, so that was the first part, how to build a quantum computer, right? And again, there's lots of different efforts in that. Second part is what problems can be solved. And at the end of the day, this is really important, right? We're not here just to solve an interesting, challenging engineering problem, although the science is really, really interesting and it's exciting. The problems are really what drives the reason to do this, right? What could you actually do with this computer? Well, I'll share a couple of things that we've actually already been able to do. In April, we published this paper in Science on really simulating a chain of magnets. Now, there have been an open question as to how a 1D chain of magnets really behaved and interacted with each other. And we were able to work with collaborators at the University of Ljubljana from Slovenia to actually simulate this system on our quantum processors today. So we were able to set that up like a 1D chain of magnets and actually resolve some of the outstanding questions that were there. Just a month before that, we published another paper in Science, and this was on engineered dissipation to entangle many-body states. So for those of you in the room who are really involved in this type of research, many people know that the interaction between qubits and their environment is fragile and actually can lead to a lot of loss of coherence, which is frustrating, right? General wisdom is that this is not a good thing for your quantum computing systems. However, in this paper in March, which we did in collaboration with the University of Geneva in Switzerland, we actually showed that we were able to specifically, intentionally engineer dissipation, so engineer the interaction between qubits and their environment to actually create a new approach to setting up many-body state for quantum entanglement. And these are just 2 examples, and here are other examples just from the past 2 years from our team working together with collaborators. And the point here is really at the top of this slide, right? Today's processors are already useful for science discoveries. Now, I want to be very clear, right? None of these discoveries are beyond what is possible on a classical computer. They certainly could have been achieved on a classical computer as well. But this is using quantum computing as another tool, right? It's using a wrench in addition to a hammer to actually get to really interesting scientific findings. And we expect that there will be many more. So one comment here, and I think you can read it even though the spacing seems a bit off, on early users on our processors. So we've had many inquiries on, are your processors open for access? Could we actually try them? We've got lots of great ideas. I would say, until now, really a lot of our focus has been on trying to push the performance of our processors because there's a lot of work to do, right? We've got orders of magnitude to go. That being said, we are working with a select set of users to really accelerate scientific discovery, build up this muscle of external access, right? Build up the reliability and the automation of our systems. It's not easy, and we have a finite set of resources, right? We can't try everything. The key is in really picking the right types of problems, knowing that we've got limited access and limited time on our quantum processors. What are the right problems that we should be trying with collaborators now, at this moment? We know lots of people have great ideas, and right now we are targeting experiments at the scientific cutting edge. So if you've got an idea, please contact us, and we'd love to hear about it and talk about it further. And then, of course, right, these are for near-term devices. Longer term, we've seen at Quantum Algorithm Zoo, right, over 60 algorithms delivering quantum speedups to date. We expect that there are many others out there, just need to see what others are working on and how they can think about this in terms of applications. We are working with many partners on developing applications for fault-tolerant computers. So what does that look like? One, you've got a milestone 5 or a milestone 6 or even better quantum computer. We want to make sure the applications are ready such that computers can be used right away. Here's the take-home point I really want to make sure gets across to each person here. I mentioned at the beginning, I talk about the 2 components of our mission and then the one thing that would be required to do this. And it's right here on the slide. Succeeding requires partnership, right? It's our firm belief no one company, no one research group, no university, national lab, country is going to be able to succeed in building a quantum computer on its own. It's going to require partnership. Highlight a couple of short examples. Talent, we've heard about this already. Obviously, it's got to be talent development, and universities and governments play an enormous role here. We are very happy to have announced the University of Chicago, University of Tokyo, Google partnership last year on the sidelines of the G7 meeting. And this is another important partnership for workforce development. I wanted to put this up on the screen just so you all had a chance to see. We've added over 100 roles to Google Quantum AI in this year alone, 2024. And oftentimes people think, oh, it's research scientists, it's maybe hardware engineers, software engineers. In fact, a lot of different skill sets are needed on our team. We really need people to be developing these skills. We really welcome lots of different backgrounds, and we are hiring. So please chat with me later today. Check out our website. Supply chain, this has been mentioned previously. You can see here, a lot of people think, wow, the secret sauce is in the processor, right? And we've heard about different approaches. At Google, our approach is superconducting qubits. We do think this is one of our unique strengths. But a lot of equipment and parts go into this, right? In the processor alone, I think many of you know this, right? The fab facility here, the fab facilities at different foundries, we've got our own. There are hundreds of instruments, equipment, and tools that go into that. No one company can be the master of all of that. We've got to work with vendors, suppliers, partners to actually have all the instruments that we need. And outside of the processor, right, you've got the package, you have the wiring, the cryostats, control electronics, the software. The list goes on. We partner with hundreds of different organizations to really bring together all the components we want to build. Security, I'll just touch on this very briefly. I think we all know that one of the potential use cases and problems that can be solved is large number factorization. Just wanted to highlight that we really appreciate the work that NIST is doing. And even though such a quantum computer that could break factorization is years away, really is important to be working on these things now. Final point, application discovery. In the 1940s and 1950s, the earliest classical computers, nobody would have predicted exactly what we use our phones, our cars, our computers, our laptops, data centers for today. Right? Nobody could have imagined that. We think it's going to be the exact same for quantum computing. What ideas are out there for application discovery? How else could and should a quantum computer be used? We've been very heartened to see a lot of effort on this in the industry. In collaboration with governments, academia. We did announce a partnership with XPRIZE earlier this year to really start to solicit lots of different ideas on these quantum algorithms and applications. I'll close on this point and then very happy to take questions. It's another quote from Richard Feynman, and the background is a picture of our lab in Santa Barbara. And he says, by golly, it's a wonderful problem because it doesn't look so easy. I'll say, even though we know where we want to go, it is a very, very difficult journey. It is arduous, it's challenging, lots of different tasks to get done, lots of unknowns, but it is a wonderful problem. We love it. We're so excited to be on this journey. Thank you.
This is a question from our virtual audience. Would you be able to talk about Google Quantum AI's recent investment in QEra, which has a different quantum modality?
Yes, happy to speak a bit about that. So just last week, we announced that we made an investment in QEra, which of course is pursuing neutral atoms. I would emphasize, and I mentioned this briefly, Google Quantum AI's priority is superconducting qubits. It's what we've been working on for the past decade plus. We really do see this as that really the best opportunity to get to fault-tolerant quantum computing for a number of reasons, in particular fabrication and also clock speed. That being said, we're always looking at all of the different approaches and the different advances that have been made in the field. In the past year, and this was mentioned in the opening statement today, but in the past year, we've been excited to look at lots of progress, including in neutral atoms. This was something we really wanted to look at, partner with, and see more what the opportunities are and that's what really drove our investment. Yes, I mean, we're certainly looking at all of them. So we're always tracking what's happening in the literature and what's happening in announcements. Neutral atoms, as I mentioned, seems like, and potentially, right, there's different advantages and disadvantages to every platform. So certainly that seems promising. We've been excited to see some of the progress in photonic quantum computing as well. Yes, and then of course, always looking at interesting ideas in semiconducting and other.
Thank you so much.